Welcome for another podcast for the Radiation Research Society. And today we have Aashish Soni from Dresden University in Essen. And we're going to be talking about PARP inhibitor and their usage for radiotherapy and radiosensitization. So, maybe you want to introduce yourself and tell us a bit about, why you've been doing this research, and give us an overview if you don't mind.
Yeah, for sure. Thank you very much. Actually, I am Aashish Soni. I am working as a postdoctoral fellow in the University of Duisburg-Essen. And I'm working in the group of George Iliakis. And this is a DNA repair lab. So we are interested in DNA repair. And why we got interested in PARP inhibitors to inhibit the alternative pathway, which we also call backup pathway of end joining. That was our main concern using PARP inhibitors initially. But later, when we screened different PARP inhibitors, we came into a very nice conclusions, for example, that they may differ in their mechanisms in the ionizing radiation-induced DNA double-strand breaks repair. So what I'm showing here and at this meeting here is the BMN 673, which is also known as talazoparib. And this is a very recent PARP inhibitor. And in comparison of the, for example, second generation PARP inhibitors, we saw very prominent effect on the DNA double-strand break repair. That is actually, so this is a very potent inhibitor, not only for the PARP1, but it affects globally the repair, what we found in this one, which can radiosensitize the cells to very much extent in comparison of other PARP inhibitors, as I say, PJ34, which is a second generation PARP inhibitor.
So, okay, PARP inhibitor. Can you, for people who don't know about DNA repair, tell me if I'm wrong, but PARP inhibitor have been used even without radiation, right?
Yes.
And so maybe you want to, can you tell us, because we want to be a bit more pedagogical in terms of this podcast, can you explain how the PARP inhibitor works? And then we'll dive into the radiation component, which is, I think, a bit newer, I would say. So.
Okay. So I should, first, the PARP1 is a poly-ADP ribosyl polymerase 1 protein.
Right.
Yeah, actually, and it is initially it is very important for the single-strand break repair. Mm-hmm. And actually, as I say, that in the double-strand break repair, what we found that the backup pathway, when the main classical non-homologous end joining and homologous recombination are somehow compromised, then the cells repair this break with a more error-prone pathway, which we call the backup pathway. And when we looked carefully in the biochemical aspects of this pathway, we found that PARP1, along with ligase 3 and ligase 1 and XRCC1 plays a very important role in this backup pathway.
I see. So basically the idea is that a tumor, because it's fairly well known to be genomically unstable, therefore it must have some kind of very strong repair processes. And the strategy then for this PARP inhibitor being used in the clinic right now is to kind of like derail the repair process of those tumors by blocking it. And so would you say that the backup pathway is the main repair pathway for tumors, or what is the current consensus? Or is it homologous recombination, or is it non-homologous unjoining? What is the classic one?
That's very, very good question, actually. As the name suggests, the backup pathway. So the main pathway in mammalian cells for the DNA double-strand break repair is the classical non-homologous end joining, which is dependent on DNA PK and COO. Actually, and when you don't have this pathway working in the cells, then you see enhanced backup pathway. So as we say, this is a backup for the main rejoining process. The cell will not opt an error-prone pathway at the first choice. So it wants to rejoin the breaks very fast, kinetics, and which is the classical non-homologous end joining is doing that. When the cell does not have this resource, then it has to somehow fix the breaks, because double-strand breaks are very lethal. And cell do not want to see them open. So it will somehow try to join them. And it does it even on the cost of a lot of errors, which are in the form of genomic instability and translocations, but it will fix them with the use of backup pathway.
So, okay, you have the PARP inhibitor. So the PARP inhibitor will affect which repair pathway the most? Is it affecting the non-homologous unjoining, the homologous recombination, or the backup, or is it affecting all three equally?
Actually, that's a very good question. Normally, the path of, for example, the PJ34, the second generation inhibitor, or the more recent inhibitor like olaparib, they inhibit backup pathway because PARP1 is the component of backup pathway. But with the BMN 673, the interesting part is that for the radiosensitization, because we wanted to check that what happens to the radiosensitization when we inhibit PARP1. And this is known for long, that if you inhibit PARP1, you see very modest radiosensitization in the cell. So that's why people are not so interested in PARP inhibitors combining with the radiotherapy, because you see very less effect there. On the same time, we found that the ionizing radiation-induced translocations, they are also made by classical, they are suppressed by classical non-homologous end joining, and the backup pathway is the main pathway which is making those translocations. Because when we inhibit PARP1, we see a significant reduction in those translocations. And this is true for example, the second generation PARP inhibitor, which we use a lot, the PJ34, olaparib, and very specific PARP1 inhibitor, AG14361. And everywhere we saw that the translocations are reduced significantly. But as I say, this BMN 673, the talazoparib, and what we were expecting, because it is shown as a single agent in breast cancer cells, that is very potent than olaparib, which is already in clinic. So we got interested that better we see much more inhibition of backup pathway using this. That was our primary goal, to use this inhibitor. And when we inhibited the PARP1 using this inhibitor, contrast to what happens with the other inhibitors, we found that there are more translocations.
So basically, the new inhibitor has a better radiosensitizer, basically.
Yes.
Do you have any hypothesis why is it so?
Actually, yes. So what we checked then, because that PARP1 does not do anything. PARP1 inhibition on DSB repair, we don't see any effect otherwise. But when we put this inhibitor, we see significant reduction in the repair also, which suggests that the classical non-homologous end joining or homologous recombination may get affected by inhibiting PARP1 with BMN 673. And this is particular for this particular inhibitor, I say. All other inhibitors are different. We also checked for the catalytic inhibition of PARP1, and when we checked PJ34 or olaparib, AG14361, BMN 673, in comparison of control, we see complete suppression of PARP1 activity. So this effect, what we see, cannot be explained on the basis of the catalytic inhibition of PARP1, but indeed, as I say, that we also see the repair defect, which otherwise we don't see with any other PARP inhibitor. So then we checked for specifically for the DSB repair, for example, with the gamma-HTX foci, and in comparison of control, and the PARP inhibitor, for example, PJ34, where we see a very nice repair after 8 hours, majority of the foci are resolved. In case of BMN 673, we see at least 70% foci are not gone.
I see.
So which show a big repair defect there.
So maybe you've been, so maybe that inhibitor is hitting a repair hub where you're really affecting multiple pathways. But then the next question comes to my mind is about toxicity, because if you've got something so general, repair is critical for healthy organs as well, right?
That's true.
So how do you think you're going to see large toxicity on the clinic with such drugs?
Actually, what we checked, that along with the sarcoma cell lines, where we saw very good radiosensitization, we also used the normal human fibroblast cells, and there we did not see any radiosensitization with BMN 673 in a broad spectrum of doses. So it is not affecting the normal cells. At least on the survival level, we have seen that.
So it must be something related. Do you think it's related to the fact that the normal fibroblasts use a certain series of repair pathways? And I'm back to this question. You're saying that one of the powerful thing about this inhibitor is that it seems to be really affecting all the repair pathway, but at the same time, if it's true, then it makes it less likely to be specific to tumors, because tumors tend to be unbalanced in their repair processes, right? So I'm a bit confused. Can you walk me through why I'm thinking wrong here? What am I doing wrong?
Why it will be more specific for the
Yeah.
tumor cells. The one thing could be, which at least that they are very fast growing cells. The tumor cells
So
are,
cell cycle.
yes, it could be the cell cycle dependent phenomenon, and because they are very actively growing, and there is a large fraction of S-phase cells. And we know that the PARP inhibitors, they, like the synthetic lethality, we know how the PARP inhibitors came into limelight because of the synthetic lethality in BRCA deficient cells, what it was published in 2005, actually in these two Nature papers back to back from Thomas Halliday and Ashworth. And this actually, one of the mechanism is the replication dependent. That if you inhibit PARP1 and you don't have homologous recombination, then you have a catastrophe and the cells are going to die. I think one of the mechanism is this, that tumor cells are more actively growing than the normal cells. And this may take the cell may take the advantage of this thing, like the normal tissues may get less affected than the tumor cells.
Interesting. So let's step out for the last few questions. Let's talk a bit about larger clinical trial, let's say. One of the things that I think would be very interesting is to, and I think some places like UCSF with actually Ashworth, who now is the head of the cancer center there, they're starting going into an initiative that looks a lot like what you guys are doing. They're trying to target specific DNA repair deficiencies in certain tumor type to actually give the right inhibitor or the right drugs to really target those tumor cells. But no one is talking about doing it with radiation, which I think would be really interesting. So where are you guys going with this now? What is your long-term goal?
Actually, we are the basic researchers. So we don't do preclinical or clinical research. Definitely we need collaborators for that. But we are so excited with our basic research, and we are more interested in finding the real mechanism behind these differences between the inhibitors. And what is in literature, at least that it is known that this BMN 673, it traps PARP1 very potently in comparison of other PARP inhibitors like olaparib. So the PARP is toxically sitting on the DNA damage site, and then maybe other pathways cannot work there.
That's right.
Right?
During the entire process.
For example, and that could be partially, at least this can be explained on this basis. Now we are checking it with the ionizing radiation, and these experiments are ongoing, that in response to radiation, whether this trapping, what is proposed, is to which extent it is also true. So we are working on that currently.
I think it would be interesting to maybe list up, and then PARP inhibitor is one, but list up a bunch of different inhibitor, and then also, so that would be one axis of research, and the other axis would be more the type of repair. So you named the three classic ones, right? The backup and the two classic ones, non-homologous and homologous. And then you create those matrices where you find, okay, this inhibitor is mostly affecting this kind of repair. So that's phase one. Phase two, you take a tumor and you characterize its repair capacity and say, this tumor is very weak in repairing in this domain, therefore, we're going to hit that domain. We're going to make sure this is the primary mechanism by which it's repairing. If we mess up this repair, we probably will destroy the tumors. Mm-hmm. So I think that's really where maybe basic research could be used to actually create this kind of table, so that at the clinic you could say, okay, backup pathway for that tumor, I'm going to take your inhibitor, and then you could imagine how you could create these kind of libraries for the clinic. So
actually, that's the idea behind that. If we know the mechanism and if we know the actual targets after DNA damage, because it's a double sword, you can say. And radiation is harmful equally, it's so useful for the radiation therapy, but it makes the cancer cells resistant.
No, it's very exciting because you can think about, normal versus tumor, and if you can you have another additional advantage that in this case is the radiation, because the radiation is sensitized, you have the cells being sensitized to radiation only with certain inhibitor in your case. So that gives you even more power. Instead of just delivering the drug and waiting for its action, now you have the drug and you can make it more potent by targeting the tumor itself. So it is really not being used much yet in the clinic. I think radiation oncology has been very much lagging when it comes to radiosensitizing agent, and it's unfortunate.
Yes, and in addition to that, I also want to mention one of our results, because in comparison of the continuous treatment with BMN 673, where we get very huge radiosensitization, we also tried it for only 1 hour treatment. And then we looked, and we got almost equal response. So even very short treatment with BMN also gives almost maximum radiosensitivity, which also is very nice and maybe a dream response in the clinic, because then you can use it for a very short time and you don't, like, you are not dependent like you did it for 24 hours or how the drug is going. You give it just for the short time, and then after that, if the cells don't see the drug, it gives you the maximum response.
Excellent. Well, I think we covered the bulk of your work. It's very interesting, and you're in a great group. So I'm a big fan of Iliakis. So
Thank you very much.
I wish you a good continuation.
Thank you.
And do you have any final thoughts that you want to share with us, or?
Actually, that as I told you, that we need to know actually the targets, and as you say, the basic research can really give those targets for. And with this inhibitor, we are very much hopeful that as the community is now thinking about PARP inhibitors with combining with radiation, maybe now we will think in this direction, that the PARP inhibitors can be very useful to combining with the radiotherapy too.
Right. Interesting. Well, thank you very much for your time.
Thank you very much indeed. Thank you.